Hi friends, I have got various messages and emails and requests as to solve this mystery. How to solve a pedigree? What is the first thought that comes when you get a pedigree like this? There's so many boxes, there are so many circles, some of them are round, some of them are boxes and some of them are colored. Now, when you get a question like this, the first thing that comes to your mind is, should I leave it or should I attend it? There is a definite concept as to how should you solve a pedigree. In this video, what I will do is I will make the entire concept of pedigree very lucid, very simplified and very conceptual. Before we start with attending a pedigree, let's first understand these signals. So some symbols you all know that there is a circle who is a female, there are a round square which is a normal male, unspecified sex is this rotated square, there are children as mentioned like this, when there is a colored box it is usually diseased, and this is a proband. Proband is that child because of which the entire family comes into the clinical existence. Okay, so this is how you detect, yes, he is diseased, so there is some problem going in the family. It's called proband. Okay, now they are obligate carriers, they are diseased but by cross sign. This is a single line showing you marriage, divorced by a line which is cut. When it is two lines, consanguineous marriage, that means there is a marriage in the same family. When you have this joining with a horizontal line, it is monozygotic twin, and this is dizygotic. When you don't have this line joining them, it's a dizygotic twin. Okay, pregnancy, miscarriage and stillborn. So these are various denotions that we use for solving a pedigree. But again, coming to the main question, when you get a pedigree like this, what do you think? Now, before I just move on to solving this mystery of pedigree, let's understand the concept here. Now, to understand the concept of pedigree, we should first understand the Mendel law. Mendel said that one gene will have two alleles. One allele will come from father and one will come from mother. So this is all about the Mendel law, also called as classical mode of inheritance. That means when we say a gene, in that gene there should be two alleles. Okay. Now, whenever you look at the progeny, Mendel said you will do a random reassortment. Let's analyze what does it mean. There are four types of Mendel inheritance: autosomal dominant, autosomal recessive, X-linked dominant and X-linked recessive. Against these four are the main pedigrees asked. Let's start with understanding the concept behind it. We'll then solve the pedigrees. Okay. Now, in this example, I have taken an autosomal dominant inheritance. Let's take it Marfan's. Okay. So what you see here is, look here. What you see is, suppose I take this as a capital M, that means I am taking capital M as a normal allele, and here I am taking the capital M small m. That means this is heterozygous and this is the normal allele. Because this is heterozygous, therefore it will be diseased because we are talking about dominant. Okay. Now, having seen this, what Mendel said was just first segregate the alleles. So from this capital M small m, I got capital M small m. From these two capital M, I got capital M and capital M. Now look at the progeny. The possible progenies are, as you see here, capital capital, capital capital, small capital and small capital. This means, look, these two are diseased because this is dominant inheritance. Okay. And because they are diseased, as you are seeing, one of the parent was diseased. Suppose I change this capital M small m to capital M capital M. This means both the parents are normal now. If you take both of them as capital M, can any child be diseased here? It is just not possible. This means there is something called as rule of dominance. The rule of dominance, what we can now say is, if any child is diseased, one of the parent must be diseased. It is not possible that in a dominant inheritance, both the parents are normal and still the child is diseased. It's just not possible. Okay. So this is the rule of dominance. Well, does this rule of dominance plays in recessive? No. See how. And here example of Gaucher's. Okay, where capital G is normal allele, small g is mutated allele, again capital and small. So you see both of these parents are normal because it's heterozygous condition. Now when you separate the alleles according to Mendel law, capital, small, capital, small. Now look what happens to progeny. Capital, 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 small, and this is small, which is a diseased condition. Now as you see, in recessive, a child can still be diseased if the parents, both parents are normal. Got the point? In recessive, a child can be diseased if both the parents are normal. That means in recessive, you can get generation skip. It is not necessary that when a child is diseased, the parent must be diseased. It is not necessary. Now we move to X-linked diseases. Let's take an example of color blindness. Let's see here. Now what you see here is, I've taken an example of color blindness. So this is XCY, this is XX, okay? XCY and XX. What you do is, we just separate out the alleles. This is XCY, and from this I get X and X. What are the possible progenies? I get XEX, XEX, XY, XY. Now what you see? What you see is, both the daughters are carriers and all the sons are normal. Who was diseased above? Who was diseased above? Male. And who is diseased now? Daughters are being carriers while the sons are normal. This means what? In X-linked disease, the male can never transmit to son. Got the point? In X-linked disease, the male will never transmit to son. And it's very logical, because look, a male or a son actually gets his Y chromosome from father. But here the disease is where? On the X chromosome. Because the son is getting his Y chromosome from father, he is not getting the mutated allele. Got the point? He is not getting the mutated allele, and therefore he will never get a disease from father. In other words, if you ever see a father transmitting to son, it is not X-linked disease. Again repeat, if you see father transmitting to son, it is not X-linked disease. So father will transmit to daughters. Got the point? Let's see now X-linked dominant. Here I have taken an example of Alport syndrome. See here XAY, so diseased male, XX normal female. So I am just segregating the alleles now. XAY, XX. Okay. Now look what is happening to progeny. XAX, XAX, XY and XY. Okay. What is happening? Diseased female, normal son. X-linked dominant. We have discussed two rules. Rule of dominance. If any child is diseased, one of the parent must be diseased. Okay. Second rule, rule of X-linked disease. Male will never transmit to son. And also note, when the male is diseased, all daughters are diseased here. All daughters are diseased here. This means, let's just quickly recapitulate my two rules. My rule number one is rule of dominance. In rule of dominance, if any child is diseased, one of the parent must be diseased. Second is rule of X-linked disease. In this rule, a male will never transmit to son. Let's now see how to solve pedigree. See here. When you get a pedigree like this, the problem is you need to think about what is the genotype of this and what is the genotype of this one. Let's assume something. Let's assume that this is dominant condition, autosomal dominant. So what is the usual way? The usual way is you take the genotype as capital M, or small m if it is autosomal dominant. Agreed? If it is autosomal recessive and it is Gaucher's disease, you take small g. Okay? If it is X-linked recessive and it is color blindness, you take it XC. And if it is X-linked dominant, it can be XAX. There are the possibilities when she is diseased. And when he is normal, suppose it is autosomal dominant, you need to take capital M, capital M. If it is autosomal recessive, capital small or capital capital, capital small, or can be capital capital. And if it is X-linked disease, XY, simple XY. Now what to do? What you would be doing is, you would be just comparing everything to everything. But that is not possible because in an exam, you have limited time. So, follow my two rules. My rule number 1, if you see a diseased child, okay, start from below. Is diseased child, any of the parent is diseased? If your answer is yes, it is dominant. So, let's try the rule here, okay. Now, this see how the things become simplified. Now, what I'll do is, I'll just ask you some questions and you need to answer it with me. See here, he is diseased, okay. Is either parent diseased? Answer is yes. He is diseased. Is either parent diseased? Answer is yes. He is diseased. Is either parent diseased? Yes. Now, they are diseased in the generation. Is either parent diseased? Yes. Because one of the parent is diseased, it straight away becomes dominant. There is no doubt, it becomes straight away dominant. Now what to do? Look for the males. Do you anywhere see a male transmitting to son? If the male is transmitted to son, look, male is given to son. Now can this be male given to son? Can this be X-linked? No, a male can never give to son in X-linked disease. So answer becomes autosomal dominant. Simple. Let's try the next one. Look here. Okay. Now try with me. Start here. So he is diseased. Is either parent diseased? Yes. He is diseased. Either parent diseased? Yes. Now look at this generation. Either parent diseased here? Answer is yes. Now look at this one and look at them. Either parent diseased? Answer is yes. Now look if you are able to see a male giving to son. Nowhere. Okay. What you see is the male given to son, you see nowhere. But here the male has transmitted to son. The male has transmitted to son. Can it be X-linked? No. What is it? It again is autosomal dominant. Why? Because male has transmitted to son. Cannot be X-linked. Next. Look here. So, again applying the same rule. Look here. So, he is diseased. Is either parent diseased? No. Diseased? Either parent diseased? No. Diseased? Either parent diseased? No. Can it be dominant? No, it is recessive because either parent is not diseased. But in this pedigree, you are not getting so much idea as to you can say it is X-linked or autosomal. So let's do one thing. Let's consider this to be X-linked recessive. I'm just considering this. Okay. So suppose, look here. Now in this pedigree, note here that suppose we consider this to be X-linked recessive. So what is the genotype of this lady? She should have XC and XC. Only then she can be diseased. Okay. So she should be XC, XC. But what about her partner? He is normal, XY. So what is the progeny? X, XC, X, XC, XC, Y, XC, Y. Now, if this is true, so all the males should be diseased, isn't it? Is it happening here? Look, all the male should be diseased. Is it happening? It's not happening. All the sons are normal here. So can it be X-linked? No. Answer is autosomal recessive. Simple. Answer is autosomal recessive. Got the point? Let's move further. See here. Look, this is a carrier state. First tell me, can you see a carrier state in dominant condition? No, it's not possible because heterozygous will manifest. So the moment you see carrier, rule out dominant. Rule out dominant. Okay? Now you see here. What you say is, look here. He is diseased. Is either parent diseased? No. Carrier is not diseased. Carrier is not diseased. Look here. Is either parent diseased? No. Look here. Is either parent diseased? No. Now look here. Is either parent diseased? No. Now when you look at them, again you see either parent is not diseased here. Look here. Is either parent diseased? No. Because either parent is not diseased, therefore it is not dominant. It is recessive. It is recessive. Okay? It is recessive. Now, what is it? For that, let's now look at if you see any male transmitting to son. So just search for it. Do you see anywhere a male transmitting to son? Look here, male to daughter. Okay? So you find nowhere a male is transmitting to son. What is it? It is X-linked recessive. Simple. Move further. Try this. Look here. He is diseased. Is either parent diseased, not diseased. Carrier is not diseased. Okay. Look here. Is either parent diseased? No. So because either parent is not diseased, can it be dominant? No. It is recessive. Now look for males. Is male giving to son? No. But male is giving to daughter. Okay. Male is not giving to son. The male is giving to daughters. Again, you see male, but there is no children here. So male is not given to son. What is it? It is X-linked recessive. Again revise. If a male gives to son, it is not X-linked. Revise with me. If male gives to son, not X-linked. Next one. Let's try here. See here. So only one of the parent has been studied and he is diseased or she is diseased. So you need to consider them to be diseased. So is either parent diseased? Yes. Either parent diseased? Yes. Either parent diseased? Yes. Either parent diseased? Yes. So every generation is showing you disease condition. What is it? It is dominant. Now see autosomal or X-linked. So see here. He is a male giving to female. But male, all the sons are normal. Isn't it? A male, all daughters are diseased. Remember my rule. If a male is diseased and all the sons are normal, well, all the daughters are getting diseased. What is it? It is X-linked dominant. It is X-linked dominant. Next. Sometimes a pedigree can fool you like this. See here, when a female is diseased, all progeny are getting diseased. Every progeny is getting diseased. Female is diseased, all progeny are diseased. Male is diseased, all the progenies are normal. That means only female is transmitting, not male. What is it? It is mitochondrial inheritance pattern. The straight away becomes mitochondrial inheritance pattern. So now I have few questions with you. If you understood it, I am just revising these rules again. If you see either parent diseased, dominant. If you see male giving to son, not X-linked, write it down. If you see male giving to son, not X-linked, and this male should transmit to all the daughters. Now see here. Tell me what is it? What do you see? When the female is diseased, all the progeny are diseased. When a female is diseased, all progeny are diseased. Female is diseased, all progeny are diseased. But when a male is diseased, none of the progeny are diseased. None of them is diseased. What is it? Mitochondrial inheritance. Quiz number 2. Tell me what is it? Apply my 2 rules. Rule number 1 is either parent diseased. Is either parent diseased? Answer is yes. Write it. dominant. Now see, is you see anywhere male given to son. Male given to son. Yes, male is given to son. Can it be X-linked? No. Autosomal dominant. Autosomal dominant. Next one. Try here. First rule. Either parent deceased. Either parent deceased. Either parent deceased. Either parent deceased. Yes. In every generation, one of the parent is deceased. What is it? It is dominant. Now look for males. Male deceased, all daughters are deceased. Remember this. Male, all daughters are deceased. Male, all daughters deceased, and all sons are normal. Got the point? So when a male is deceased, daughters are deceased, but not son. Male not given to son. Obviously, X-linked dominant. X-linked dominant. So, when you get a pedigree, just apply my 2 rules. I am Dr. Praveen. I just made it very simple. 2 rules means write it down again. Whenever you see one of the parent deceased, dominant. If you see male giving to son, not X-linked, but male will give to all the daughters. This is how you solve pedigree, and I think you can make it very simplified now. My suggestion for you is to just revise this pedigree again and again, rather than going to Google, which will just confuse you. Just solve pedigree in the way I told you. More conceptual, very lucid, and very easy to understand.